Welcome to your first video for organic chemistry. Today we're going to start with the review of Lewis structures. So hopefully you'll remember some of this from way back in Chem 123. We're going to start with water or H2O. And remember that for Lewis structures you need to first count the number of valence electrons, which we can look up on the periodic table. So oxygen is in group 6, and so it has 6 valence electrons. There are 2 hydrogen atoms, each of which have 1 valence electron because it's in group 1, for a total of 8 valence electrons. When we start thinking about Lewis structures, hydrogen can only form 1 bond, and so it's never the central atom. And so oxygen must be our central atom in this Lewis structure. And so I'm going to start with oxygen, and I'm going to put the 2 hydrogens around it. We can connect those hydrogens with a bond, and each bond, remember, represents 2 electrons. And so I have used 4 of my 8 electrons in bonds. And remember that hydrogen can only hold 2 electrons. It's an exception. And so hydrogen is finished. But I have 4 remaining electrons that I can use to complete the octet of oxygen. And so I'm going to put in 2 lone pairs on oxygen, which completes the octet and uses the remaining 4 electrons I had left over. And so I'm left with 0 electrons, and my Lewis structure for water is complete. If we move on to the simplest organic molecule, that's going to be CH4, or methane. Carbon is in group 4, and so it's going to give us 4 valence electrons. Hydrogen is still in group 1, but this time we have 4 of them. And so we're left again with 8 valence electrons. Again, hydrogen can never be the center of our molecule, and so we're going to put carbon in the center and spread out the hydrogens around it. Methane is a tetrahedral molecule. And so to show shape here, we're going to use a heavy wedged bond to indicate that that hydrogen is coming out of the page towards us. And we're going to use a hash mark bond to indicate that that hydrogen is going back into the page away from us. Importantly, we're not going to use a dashed bond like this. That indicates something very specific in chemistry, and we don't want to use it. And so we are going to make sure that this is a wedged hash mark bond like that. Remember, each bond accounts for 2 electrons. So I have 4 bonds, that's 8 total electrons. And so I've used all my electrons. Each hydrogen has 1 bond, so that's 2 electrons each for hydrogen, which is good. And the carbon has 4 bonds, which is 8 electrons completing its octet. And so that Lewis structure for methane is complete. Let's do a little more practice with nitric acid, or HNO3. Remember that the first rule of Lewis structures is you're going to calculate the number of valence electrons that are available to you. And so you've got 1 hydrogen. Hydrogen has 1 electron. You've got 1 nitrogen. Nitrogen is in group 5 of the periodic table, and so you have 5 electrons from nitrogen. And you have 3 oxygens. Oxygen is in group 6, and so you have 6 electrons from each oxygen, or 18 total electrons from oxygen, which gives us 24 electrons in the Lewis structure. The next thing we're going to do is to double check any sorts of formal charges. If you had a charge in this molecule, for every positive charge, you remove an electron. For every negative charge, you should add an electron. The next thing you want to do is draw the skeletal structure. Often, skeletal structures are symmetric. Usually, the least electronegative atom goes in the center. The exception to that, of course, is hydrogen. We've already talked about that. And so the least electronegative atom in nitric acid then outside of hydrogen is nitrogen. And so we're going to put nitrogen in the center. The remaining atoms are often spread evenly around. And so I'm going to start with the 3 oxygens. And nitric acid is an oxo acid. And in oxoacids, those are just acids that contain one element plus oxygen plus a hydrogen. And in oxoacids, the hydrogen is connected to oxygen, not the other element. And so I'm going to add hydrogen to an oxygen now. I'm going to count up my total number of electrons that I've used so far. So 2, 4, 6, 8 electrons from bonds. And that leaves me with a total of 16 electrons remaining to use. I'm then going to start distributing those electrons around, starting with the perimeter atoms first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've completed I've used all of my electrons. I need to now check and see if every atom has an octet. And I noticed that my nitrogen atom in the center does not have an octet. It only has 3 electrons or 3 bonds around it. So that's 6 total electrons. And so to complete that octet, I'm going to take one of my oxygens, lone pair, and I'm going to share it with nitrogen. The last thing we need to do is consider formal charge. The formal charge of an atom is equal to the number of valence electrons minus the number of bonds minus the number of electrons on that atom. And so if I look at this oxygen has 6 valence electrons, and I'm going to subtract the number of bonds. It's got 1 bond, and it's got 1, 2, 3, 4, 5, 6 electrons around it. And so I'm going to subtract 6 from that, and I get -1. So oxygen with 3 lone pairs has a -1 formal charge. If I look at an oxygen that has 2 lone pairs, like the one down here, again, it's got 6 electrons minus 2 bonds minus 4 electrons and lone pairs is equal to 0. And so that oxygen has a 0 formal charge, and we do not need to worry about writing in 0 formal charges. If we look at nitrogen, nitrogen has 5 valence electrons. It's got 1, 2, 3, 4 bonds around it and no lone pairs. So that gives me a formal charge of +1. So this nitrogen has a positive formal charge. In all neutral molecules, the formal charges must add up to 0. For ions, the formal charges must add up to the charge of that ion. When thinking about Lewis structures, most atoms have an octet, but there are a few exceptions to the octet rule. We've already talked about hydrogen. Hydrogen only has 2 electrons, always. Boron and aluminum are another exception. These atoms can only have 6 electrons. Let's consider both BH3, which is a neutral molecule, and BH4 minus, which is a negative anion. Both of these exist. If we look at BH3, we're going to put boron in the center and spread out the hydrogens around it. Boron is in group 3, so it has 3 electrons. Hydrogen is in group 1, but we have 3 of them, so that's another 3 electrons. That's 6 total electrons. And I've already used 2, 4, 6 electrons in my Lewis structure. This Lewis structure is complete, although boron doesn't have an octet. If we look at the formal charge, boron had 3 valence electrons and we're going to subtract the number of bonds, that's 3 electrons. And so the formal charge on boron in BH3 is 0. If we look at BH4 minus, this is the first anion we've looked at. And so again, boron has 3 electrons. Hydrogen, we have 4 electrons from hydrogen. And we have 1 extra electron from the negative charge. That gives me a total of 8 electrons to use. Again, I'm going to put boron in the center and spread my hydrogens around. And I've used 2, 4, 6, 8 electrons. I've used all my electrons. But now the formal charge on boron, I started with 3 electrons. I'm supposed to subtract 4, 1 for each bond, and that gives me a -1. So the formal charge on boron is -1. Note that the formal charge totals the charge of the ion with -1. And so boron and aluminum both either are neutral and don't have an octet, or they're negatively charged and have an octet. The last exception to the octet rule that we'll talk about is sulfur, or really elements in period 3 and below. These can expand their octet. We're going to look at H2SO4 as our example. H2SO4 is another oxo acid, and so we're going to pick the least electronegative atom outside of hydrogen, that's sulfur, put it in the center. We're going to spread out our oxygens around the sulfur. And then remember, in oxo acids, the hydrogens are connected to the oxygens, not the sulfur. I'm going to count up the total number of electrons. So sulfur is also in group 6, and so it has 6 electrons. Oxygen is in group 6, but we have 4 of them, so 6 electrons each. And then hydrogen, we have 2 of them at 1 electron each. So we have 6 times 4 is 24, plus 4 is 30, plus 2 is 32 electrons. We've already used 2, 4, 6, 8, 10, 12 electrons in bonds. So that gives me 20 electrons remaining. I'm going to start by distributing those around, starting with the outside molecules or atoms. So 1, 2, 3, 4, 5, 6 completes oxygen's octet. 1, 2, 3, 4, 5, 6 completes that oxygen's octet. And so we've used 12 of the 20 electrons. 1, 2, 3, 4 uses another 4 of those electrons. And 1, 2, 3, 4 uses the last 4 of those electrons. So I've used all of my electrons in this structure. If I look at formal charge, this oxygen we saw earlier had 3 lone pairs was equal to a negative formal charge. Let's do that again. Oxygen has 6 valence electrons. It's got 1 bond. It's got 6 electrons around it. That gives me -1. So any oxygen that has 3 lone pairs and 1 bond is going to have a -1 formal charge. Oxygens with 2 lone pairs, again, start with 6 valence electrons, but they form 2 bonds and only have 4 electrons around them. So that gets me a 0 formal charge. Sulfur has 6 valence electrons. It has 4 bonds and no lone pairs. And so it's got a formal charge as drawn as +2. Anytime you have a +2 formal charge next to a minus formal charge with either empty space, we haven't completed the octet, or an element in group 3 and below, we can expand that octet and use a multiple bond to satisfy that. And so I'm going to take away 1 lone pair from oxygen and share it with sulfur. And that's going to give me a neutral charge on that oxygen. I'm going to repeat that on the other side. take a lone pair away, and share it with sulfur. So now in the new sulfur structure, sulfur still has 6 valence electrons, but now it has 6 bonds, and so its formal charge is 0. And so this is often the Lewis structure that you will see for sulfuric acid, where all the formal charges are 0, but the sulfur has an expanded octet. The process that we use to draw the Lewis structure of nitric acid and sulfuric acid can be super useful for molecules that are new to us. But it can also be useful to be aware of some general trends in Lewis structures or bonding patterns for atoms. So hydrogen is in group 1, and so it is going to form one bond, as in H2. That's the complete Lewis structure for H2. We're going to skip group 2 because we don't typically see Lewis structures formed with group 2 atoms as they form mostly ionic bonds, and go to group 3, or boron. Boron is in group 3, and so typically we just saw if it's neutral, it's going to form 3 bonds, as in BH3. Carbon, we've seen a couple of times, is in group 4, and so it typically forms 4 bonds, as in methane, which we have already seen today. Nitrogen is in group 5, but it does not form 5 bonds. Group 5 atoms tend to form 3 bonds. We're going back down, as in ammonia. Ammonia has a lone pair on nitrogen and 3 bonds to hydrogen. Oxygen in group 6. I forgot my 5 up there for nitrogen and my 4 for carbon. Oxygen is in group 6, and it tends to form 2 bonds. We've seen that in water already. And any halogen, we're going to use fluorine as an example. In group 7, tends to form 1 bond, as in HF, and it has 3 lone pairs around it. So it can be useful to recognize patterns in bonding so that you can quickly identify Lewis structures that are correct or Lewis structures that look a little bit funny. Now let's apply our knowledge of bonding to drawing the Lewis structure for C2H6, or ethane. Often in organic chemistry, you will see this written as CH3, CH3. This is known as a condensed structural formula, which is super useful because it indicates connectivity, or how the molecule is connected together. This is going to indicate the skeletal structure of connectivity, and so what this tells me is this CH3 is a carbon with 3 hydrogens attached to it. That CH3 is connected to another carbon that also has 3 hydrogens attached to it. So just visually inspecting, every hydrogen has 1 bond, so that's 2 electrons. So that's what we want. Every carbon has 1, 2, 3, 4 bonds. And so that is also what we were looking for carbon. That completes an octet because every bond is 2 electrons. Let's look at one where the octet rule is not automatically complete. And so let's look at CH2CH2, or ethene. Remember, this is the condensed structural formula, and so it's showing me the connectivity. And so I know I have a carbon that's connected to 2 hydrogens that is also connected to another carbon with 2 hydrogens. And so if I look at this, just looking, every hydrogen has one bond, and that's to be expected, but the two carbons only have three bonds. And so to complete that, I am going to use a double bond to give both carbons an octet. We can always use the total number of electrons to double check that that's accurate. And so if we look at this, we have two carbons, both with 4 electrons. I have 4 hydrogens, all with 1 electron. And so that gives me a total of 12 electrons. If I look at my structure, I have 1, 2, 3, 4, 5, 6 bonds. 6 bonds times 2 electrons each is equal to 12 electrons. And so these numbers match. And this is the correct structure for ethene. If we get a little more complicated, we can look at ethanol, or CH3, CH2, OH. The process is still the same. This is the condensed structural formula of the molecule. And so I know I have one carbon that's attached to 3 hydrogens that is attached to a carbon that's attached to 2 hydrogens that is attached to oxygen that's attached to 1 hydrogen. If I look at this, I've got all hydrogens have 1 bond. That's a good thing. All carbons have 4 bonds, which means it has an octet. That's a good thing. My oxygen has 2 bonds, which is a good thing, but it doesn't have an octet. And so to complete its octet, I'm going to give it 2 lone pairs of electrons. Using the same process that we did for ethene on the previous slide, double check that the number of electrons in our Lewis structure matches the expected number of electrons if you count all the valence electrons in the molecule. The last topic for today's video is resonance. Resonance occurs when there are multiple Lewis structures to represent the same molecule. Let's start with the acetate ion, or CH3CO2 minus. The first thing we're going to do is notice that I have a CH3, and so I'm going to write a C with 3 H's attached, which is directly connected to a carbon that has 2 oxygens attached. The first carbon on the left is done. It's got 4 bonds to it. The hydrogens are done. They have 4 bonds to them. The next carbon only has 3 bonds, and so I'm going to use a multiple bond to complete its octet. Oxygen on the top then has 2 pairs of electrons to complete its octet. And the oxygen on the right needs 3 pairs of electrons to complete its octet. If I go through and assign formal charge, the top oxygen has 6 valence electrons minus 2 bonds minus 4 lone electrons is equal to 0. We've seen that several times where oxygen with 2 bonds and 2 pairs of electrons has a formal charge of 0. The oxygen below still has 6 electrons, but now only has 1 bond and 6 lone electrons, or -1. I'm going to put in my -1 formal charge there. And that corresponds to the negative sign that we saw with acetate. Now, when I drew this, I had this formula, structural formula, and I just decided to use the top oxygen to make a double bond with carbon. Why didn't I use the bottom oxygen to make a double bond with carbon? The truth is, both of those are valid Lewis structures, and so to completely represent the molecule, I need to draw both. I'm going to complete the octets just like I did before, and I'm going to complete the formal charge where I put a negative sign on the oxygen that has one bond and 3 lone pairs. The last thing I'm going to do to indicate that these are resonance structures and put this in brackets, what these brackets tell me in combination with this arrow here is that both of these structures represent the same molecule and that the actual molecule is some average between the two. That wraps up this video. Take a stab at drawing the next 3 Lewis structures on your own, and we will use one of those as your Plicker question at the beginning of the next class.